Computer Science Department, and I am a proud alumni of USIM 2019 class. So I am very proud of my study at USIM and my great supervisors, Dr. Farida and Dr. Azni. Today, inshallah, I wish you have good time with us today. Hopefully, it's not so boring, and hopefully you will enjoy this session. We'll talk. We'll take a good chunk of steganography, and specifically in a specific audio steganography. We'll take a good dose at this subject, and hopefully it will be concise and easy to understand and direct.
Ahmed, actually, we can see your presenter screen.
Oh.
Yeah.
Okay.
Yep. Okay.
Okay. So the outline of this session will be as follows. We will talk briefly about information security and how can steganography relate to information security. We will talk about the types and the scope that we will cover today, the types of steganography in general, and the scope of the today's session. We will talk briefly about the major methods in audio steganography. We will talk about how we can evaluate performance in audio steganography, what are the main performance aspects, and what are the trade-offs among these aspects. We will talk about the taxonomy in audio steganography methods, and how would we classify the methods that were proposed in audio steganography over the literature. We will talk about the most significant methods that really did some change in the area, and we will talk about how do we evaluate the methods, a brief on the contributions and the future directions in this trend. Okay, so as we all know, the information security is related to the CIA or the CIA triad: confidentiality, integrity, and availability. As we all know, the main goal of cryptography is to render information unreadable for unauthorized users. So the main goal here in cryptography is to target, or the basic goal or the first goal is to target the confidentiality in the CIA triad. The steganography targets also the same thing, the same value of the CIA triad, but it deals with it differently. Steganography secure information by obscurity. What do we mean by obscurity? We mean that if you send if we consider the cryptography will send a secret message. Alice will send an encrypted message to Bob. An attacker or an intruder will see and capture the encrypted message and will know about its existence, and he could relate the actions of Bob to the encrypted message, maybe. However, in steganography, the goal is to hide the existence of the message so that the attacker wouldn't know that there was an encrypted message in the first place or a secret message in the first place. Steganography uses innocent cover, file, or signal to hide secret information. Modern steganography varies depending on the type of cover used. So basically, we are using audio, image, and text steganography, although there are many other types of steganography: packet and VoIP, voice over IP, and many types of steganography. And any innocent cover can be used as a base for steganography, actually. However, in this workshop or in this seminar, we will be focusing only on audio steganography, where a secret message is concealed within a chosen audio signal. So basically, this is my main research area, and we will stick with it during this webinar. As we can see in this slide, here we can see a man who plays the flute, and all the children here are listening happily to the music or the tunes, noticing nothing unusual. However, for the kid here who has the key, where we call it in our area the intended recipient, he has the key and he has the way to decipher, if we can say, decipher these encrypted tunes with the music stream. He can understand the intended message. By the way, this slide was submitted and won the best slide award in 3-minute thesis in 2018, I think. I was representing USIM, and I was able to achieve the best slide during this competition. Moving forward, the hiding is done in a way that the presence of the secret message is not suspected by any users, as we can see in this slide here. So the main goal is that the existence of the message is denied or is secured, but it can be easily extracted by the intended recipient with the correct key. So only the intended recipient can understand the message. We will talk about some concepts in audio steganography. The first concept, or the terminology, concepts or terms in audio steganography. The cover signal is the original signal. The stego signal is the signal after adding the secret information. And the sample rate is the number of audio samples per second. So for example, when we see the sample rate equals 44.1 kHz, which is the CD quality, we know that there are 44,100 samples per second. That represents 1 time second. This is a huge number because we are considering uncompressed audio signal or wave format. For the depth or the sample depth, we are talking about the number of bits per audio sample. For example, 16 audio sample bit or 8 audio sample bit, 8-bit audio sample or 16-bit audio sample. So this is the resolution or the depth of the sample. The payload is the information to be embedded, or the message itself, or the secret information. Many names for the payload. Embedding, what is the embedding? Is the process of hiding the payload in the cover signal. The embedding error, it means that embedding a certain bit caused a flip in the original bit status. So the embedding error here, we doesn't mean necessarily that there have been an error in embedding, or the embedding process failed, but we mean that the embedding caused a flip in the status of the original bit in the cover signal. Audio steganalysis is the art and science of detecting hidden information in audio signals. So this is the balance in steganography methods. We have to have a steganalysis to evaluate and understand the security of the steganography methods. The embedding efficiency is probably the most advanced concept here, which we refer to the number of cover bits that are affected in embedding 1 bit of the payload. So basically, when we are hiding 1 message bit, 1 bit of the message, so we need to have as less as possible of cover signals that are affected by that change. So if we have a low number of bits that are affected by that change, this means that it is efficient. If the number is high, this means that the method of embedding is not so efficient, or it's aimed toward robustness more than transparency, as we will see later on during this webinar. The error magnitude is the severity of embedding error. How severe is the error and how destructive it was on the quality of the signal. Okay, here is a simple overview of the audio steganography process. On the left, we can see the levels, the input level, the processing level, and the output level. The first guy over here on the left is the sender or the encoder, and on the right we have the receiver, and we have the attacker in the middle. The sender starts with the message and the cover signal, and he runs the embedding code to achieve or to recognize the stego signal. Over here, the stego signal will be sent using an untrusted communication channel over to the receiver. The attacker over here can only see the stego signal, and he cannot understand what's the meaning or the content of this signal. However, the receiver can use the stego signal to run the retrieval code and retrieve the message. Audio steganography methods. So we will talk briefly about these methods. I understand it's not the time and it's not efficient to explain all the methods of audio steganography in this session. It's not an easy process. However, we will explain the most prominent or the most common methods in audio steganography. The most common method is the least significant bit, or LSB substitution. The least significant bit substitution involves replacing the least significant bit of the audio samples or the audio data with the secret data. For example, the numbers here are in Indian representation. I'm not sure why. For example, if we have the message hello and followed by space, for each letter, the ASCII representation for it will be represented in binary, and then these binary values will replace the sample values. So these are the audio sample values, and these sample values will be represented in binary representation. Finally, for each bit over here, we will use one sample in the audio signal to replace one bit. So basically, the most common method in audio steganography that is used right now is the least significant bit. It's not very easy to detect if it's used wisely, and it's not the most secure, and definitely not the most complex. The spread spectrum, on the other hand, is a method that is used for robustness, and in this method, each message bit, for example, the H here or the E, is modulated number of times to achieve a secret sequence, and this secret sequence will be embedded in the signal, in the audio signal. It's used to achieve a replication or a replicas of the message bit, so that it will be secure for attackers to destroy the embedded message. So it's basically the spread spectrum is aimed for robustness, not for transparency or less error. Okay, let's talk about phase coding. In this method, the frequencies or a certain frequencies, the phase of certain frequencies in audio signal is altered to represent the hidden data, the hidden data. So the main idea here is that we have a short or a difference between this phase and the other phase, and we want to make a certain phase to represent a certain value that represent a certain message bit. For example, for this frequency, we have the phase as 90 degrees, and to embed, for example, 0, we might keep it as 90. But if we want to make it 1, we might change this phase to be 180, for example, to represent the 1. In the echo hiding, an inaudible echo is added to the audio signal to present the hidden data, to represent the hidden data. It's actually one of the earliest methods in audio steganography, and right now the usage or the population or the popularity of this method is very low because it's not that secure and it's easily detected and destroyed by signal attacks. Okay, so what are the main performance aspects in audio steganography? As we know, the capacity refers to the amount of data that can be hidden within an audio signal. So this here is the scaling factor, how much you can add. We are basically using the audio signal as a vessel, and we want to include or to accommodate large messages inside this audio signal. So the capacity is the scaling factor among the other quality factors. The other one is the imperceptibility, which refers to how well the data are hidden and the added distortion to the signal. Basically, the quality of embedding. Basically, the quality of embedding. If we are creating low distortion, then this is considered an imperceptible method. And if we are creating a huge amount of damage on the signal, this means that the signal is, or the method is imperceptible. The method is creating perceptible noise. Sorry. The robustness, on the other hand, measures the ability of the hidden data to withstand various signal processing attacks without being lost or corrupted. So basically, in the robustness factor, we are subjecting the signal to signal attacks such as noise addition, compression, filtering, low-pass filtering, high-pass filtering, and we want to see if the embedded bits or the embedded message can withstand these attacks without being destroyed or corrupted. So different factors. The imperceptibility is the quality of embedding. How perceptible is the resultant error after embedding. The capacity is how much you can embed in this audio, and the robustness, how we can withstand the errors. The security is actually affects all of these, and it relates to the ability of the steganographic system to protect the hidden information from the unauthorized access or detection. So the security, excuse me, if you have any question, you are more than free to interrupt me. Okay. So the security is actually, as we said, can affect all of the other factors. And we can see from this figure that we have a trade-off among these aspects. And the actual trade-off is is what makes this area an interesting and a balanced area, because without this trade-off, uh, the research in this area, I don't think will be lasting so long. So basically, to increase the capacity, if we are increasing the capacity, we are taking performance point out of the robustness and the transparency. And if we are increasing the imperceptibility, by the way, is the same as transparency. Transparency and imperceptibility are the same concept. Uh, so if we are increasing or improving the transparency, the other factors or the other aspects, the robustness and the capacity, will be reduced automatically, and similarly for the robustness. However, there are some methods that we are using to improve or to optimize the performance. Okay. For example, the compression, if we are using the payload compression, like half-my encoding and run length encoding or any other compression method, in the capacity it will be increased. If we are using the imperceptibility, the syndrome trails codes, and the matrix embedding, the F5 algorithm, are the most bright algorithms regarding the efficiency of embedding. And we will talk maybe shortly about these methods in the end if you are interested. Regarding the robustness, we are using the spread spectrum to provide replicas of the embedded message, so that it can be it can resist more of the of the attacks. Okay, so let's talk about the trade-off one more time. So the embedding capacity versus the robustness. As we can see, increasing the embedding capacity, the amount of data that can be hidden, often comes at the expense of robustness. Techniques that embed more data may introduce more noticeable changes to the audio signal, making it harder to resist signal attacks such as filtering, noise addition, and compression. Conversely, aiming for high resistance against signal attacks requires, or often, dictates the embedding capacity, dictates the lowered embedding capacity. There's a mistake here. Dictates the embedding capacity to be lowered. Sorry. For the second trade-off, the imperceptibility versus the capacity, maintaining the imperceptibility of the audio signal is crucial to prevent suspicion. However, increasing the payload, the amount of hidden data, might require more significant alteration to the audio signal, potentially compromising its perceptual quality. There is a trade-off between hiding more data and maintaining the naturalness of the audio signal. So this is a very important, very important trade-off over here, and it's the most targeted in most of the literature. The third trade-off is not a very direct, however, it is exists. To attain robustness, embedding data into the signal's prominent component is crucial to endure signal attacks. So actually, this needs a little bit of explaining. If we are improving or targeting the robustness, we must target the most prominent parts of the signal, because these are the parts that can resist the signal attacks. If we are targeting targeting a small signal of speech. So the data that are embedded in the silent intervals or in the silent parts of the segment will be destroyed directly by simple attacks. However, if the data are hidden in the segments of the signal that the speaker is talking, these are the least segments to be destroyed, and therefore these are the most prominent components of the signal, and therefore to achieve high robustness, the signal's prominent components is targeted. Therefore, as a result, causing considerable signal distortion and reducing the imperceptibility. This is the main point in this trade-off. Conversely, prioritizing the imperceptibility necessitates minimal signal alteration during embedding. So if we are targeting the imperceptibility, the least significant bits of the least significant parts of the signals must be used, because we want the change or the error to be minimal, because we are targeting the imperceptibility, rendering the embedded message vulnerable to destruction by signal attacks such as noise addition and compression. So these are three trade-offs, and as we introduced, improving one aspect is reflected negatively on the other two. Okay. So regarding the taxonomy in audio steganography, the main classification criteria can be classified into three main criteria of classification. The first one is the embedding domain. The second one is the embedding behavior. And the third one is the method of data injection. In the domain, if we classify the steganography methods based on domain, we will have the time domain methods, the wavelet domain methods, and the frequency domain methods. We can talk more about these methods. However, to be concise, we can say that time domain uses the spatial or the temporal representation of the signal, meaning that for each second we can see what are the bits or the samples that represent that second, and we can work on these representations of data to embed the message. For the wavelet sake, we are talking about the discrete wavelet transform. Could be the discrete or the integer wavelet transform. We are basically converting the signal into the wavelet component, and normally we are splitting the signal into the approximate and the details, and normally we are using multiple levels of analysis to achieve or to recognize the third level of details, and then the third level of details are used to embed the message. Why do we use the third level? Why do we use the second level? It's based on the choice or the design of the author. Basically, we are trying to achieve a low and a high efficiency embedding. So, for example, if we took the bit, the least significant bit substitution, for example, for each message bit, we are changing one bit in the audio signal. So the ratio for this method is 1:1 if we are considering bits as the standard. However, if we are using the wavelet, maybe the change that we are doing in the third level of analysis and the third details level, that amount of change can be less than 1, and this is actually can do a better better efficiency. So for each message bit, we are losing an error of maybe 0.8 or 0.7. So this can be a good method. For the sake of frequency domain, we can use the amplitude modification or the phase coding. In either methods, we are targeting robustness, and we are aiming for a more robust method, not a very transparent or imperceptible method. Regarding the embedding behavior, we are talking about how each method is conducted, or what is the main idea in these groups of methods. For the first one, we have the linear. In the linear embedding, the method visits each sample or each data bank of the signal one by one linearly until the whole message is embedded. In the selective embedding, the method selects the embedding locations based on a special criteria. Could be the amplitude, could be the phase of the signal, could be a special condition, a threshold that is used to select the embedding locations. The pattern matching is a method that uses uh, an algorithm to match parts of the message to another parts of the cover signal, so that it can decrease or lower the amount of error. In phase coding, we explained how phase coding as split spectrum work. Finally, the method of data injection. So in this criteria, we are considering the actual injection point. How is this method actually substitute or inject the message bit inside the audio signal? We considered, or we talked about, the least significant bit. It's maybe the most significant or the most popular choice. However, we have the QIM, the quantized index modulation. In this method, the modulation is based on, the quantization is based on an adaptive value. So the amount of error is tunable. We can change the amount of error to the degree that we think is suitable. For the F5 algorithm or the matrix embedding, we are actually breaking the one-to-one ratio between the message and the cover signal bits. We are talking about embedding multiple errors, multiple message bits, 2 or 3, 4 message bits, using only one change or one error in the cover signal, which is a great invention at that time for transparency. It can reduce the amount of errors significantly. And finally, we have the syndrome trellis codes, or the STC. The STC came up in 2013, I believe, and it was since then it was the go-to method in many of the advanced methods in audio steganography. So we are trying to even lower the ratio between the message and the cover signal. Basically, this method is, if we know the cyclic error correcting methods, in this method we are correcting the error. However, the error are the message itself that embedded in the signal. It's far more complex to explain in this slide, so we will just move on of explaining the F5 and the SDC. The evaluation of audio steganography. We have the error rate, which can be for the capacity we can be measured by embedding by the embedding rate, or the capacity can be measured by the embedding rate, or ER, which is the number of bits embedded in 1 second of audio. So as much as we can, as much embedding as much bits to embed as we can embed, it's better. Sorry. So we are trying to embed as much as we can. Regarding the imperceptibility, it can be measured in using the signal to noise ratio, or the SNR, between the original signal and the stego signal. So basically all the quality metrics can be used to measure the imperceptibility. However, regarding the robustness, to measure the robustness, we have to subject the stego signal to a type of attack, such as noise addition, compression, low pass filtering, and so forth. And then we do a bit error rate on the recovered signal, or the recovered extracted message, to calculate how destructive was the attack on the embedded information. Of course, we want the message to be safe and not destructed by the attack, and we want the embedded message to be as robust as possible. To measure the security, or to test the security of the message, we must test the embedding method against detection steganalisis methods, such as the Markov and the MFCC methods, and so forth. There are some used or well-known methods for steganalisis that can statistically create a method of how secure your or how detectable your embedding is. Finally, we are directing, in this slide, we are directing contributions, or giving the most important directions regarding steganography. The compression is a great direction. Any compression method can be used to improve the capacity and the robustness can improve the capacity and the transparency, or the imperceptibility method. The error correction, such as the matrix embedding and the syndrome trellis codes, these are most trending algorithms regarding the efficiency in audio steganography, regarding the core audio steganography, or the core steganography in general inventions. So major directions or major efforts are done on these two algorithms, improving and optimizing. Moreover, the encoder encryption and compressed signal steganography, such as steganography in compressed signal, or encoders such as voice over IP and other coders. These are some of the most important references if you want to capture. I would like to thank you very much for your attending, and I am ready for any questions if you have any.
Thank you, Ahmed, for your talk. I think now it's time to open the floor for any questions. We have undergraduate and also researchers, our postgraduate as well. Any questions? Yeah. Takyudin. he's also a master student doing Stega right now.
Nice. Good.
Sorry, my mistake. I mistakenly. But
You have any question?
overall,
Yep.
yeah, good. What we call good presentation. I forgot I want to ask what. Sorry.
It's okay.
Ahmed,
It's okay, sorry.
since we have several undergraduate students,
Yes.
we don't have the steganography subject here, right? So we only have cryptography, but I think Dr. Hasni has embedded several topics on it lah. But can you maybe suggest on how they can like start their project or start their research on like simple research on steganography maybe?
Okay. So basically, what do we have? What we are using in steganography is MATLAB. Is the MATLAB environment. I'm sure everyone uses MATLAB. However, there is a simple function in MATLAB. It's called bit set. MATLAB. So if we are trying to and BitKit MATLAB. Okay. So basically, if we are using MATLAB, we can read an audio signal simply by using the audio read, or there is also a function in MATLAB called audio read. MATLAB. Okay, read an audio file. So we are storing in this using this function. We can just store the audio signal itself in Y and the frequency of the signal in Fs, and basically we can start changing if we know basic programming. We can change a stream of text into binary, right? Into a vector of binary, and then we can use a loop to just change using the bit set. We are setting the bit in A to be the same bit in the message, so that we can embed the whole message in B. And after we finish the bit setting operation, we can just do the audio write MATLAB. We can use the signal that we just modified, and we can do the audio write to write the new file. I'm sure there is a simple LSP. 1 second, doctor. LSP. Okay. I think there is a code over here for free that can teach you how to do simple LSP modification. It's actually very simple to do. Okay. 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 This is Objective C. No. This is Not MATLAB. Okay. Not this one. Okay, I will make sure that I will, if you want, I can visit this meeting later, and I will add a simple file, simple MATLAB file to embed and to retrieve a simple message out of the audio signal. Okay.
Okay. Thank you, Ahmed. Any questions? Any other questions from the floor?
Jabbar, you can ask a question. Jabbar.
Is that your student?
Yeah, Mr. Jabbar. He's a bit shy. It's okay.
Okay. If there is no other question, can I share the salam.
السلام ورحمة الله.
حياك الله دكتور، كيف اخباركم؟
اهلا بيك، حياك. تفضل.
دكتور، هي الدكتورة تسأل عن الكود بتاع الاوديو ستيغنوغرافي، الاخفاء ولا لا؟
ايه. عندك جاهز ترسل لي؟ انا ما اريد افتح الواتساب اللي قدام الناس. ارسل لي اياه على الايميل عندك. اعطيك.
هي لحظة دكتور. بتاع التضمين وامبيدت ولا لا؟ دزيتها لي.
نعم.
هي دكتور لحظة.
You need to translate that. You need to translate that to us, Ahmed.
1 second. Yeah, sure. He's talking about the code. I already sent it to him, so I will just check his chat, my chat with him. 1 second. He's trying to fix the problem, actually, not ask a new question. Okay.
So are we going to wait for him to do something?
Yeah, 1 second.
Okay.
I'm going to send it really quick. Maybe we can take a look on it. I'm still waiting for the. You said there's a master student. He has a question. So
In the meantime, can I share the QR code for the attendance?
Sure.
Let me share the screen. Can you see my screen now on the QR code?
Yeah.
Okay. So those who attended today, I think we shall send you the certificate for attendance. So kindly scan your this QR code and fill up the form.
خلاص يا جبر، لقيت. اسكر المايك لو سمحت.
So Ahmed, you're still going to share the code?
Yeah, I will. Can I share now?
Yes, sure.
Okay, so this is the least significant bit encoding method, and I will talk you through it very quickly.
Okay.
Okay, so over here, this section is just to read the and select using the user interface selection file. Just browse the file and select it. Okay, so here is the message. As you can see, I selected a very long random gibberish message, and over here is the processing of that message. We are converting this message into an array. This array is of certain length and width, and then we will read the audio file one more time. Actually, this part is not very we don't need it. We can read the file either this method or this method. We can use the audio read, or we can use the file read using, if we know the quality of the audio, it's 16-bit, and what is the frequency of the signal. We can use either this reading method or this reading method. Okay, so this line over here is the embedding. The embedding of the least significant bit is done using this one line only. Don't think it's a very hard stuff. It's just the data from 1 until the length of the message. We are doing the bit set function, data of 1 until len2. Replace these points of data with Q. Q is the level of embedding. We are using 1. It means the least significant bit. Using the EM message or the embedded message from 1 until length 2, or length 2 is the length of the message. So basically, it's just a replacement process. We don't need even a loop or anything like that. So just this single line, we are doing the least significant bit embedding. Over here, we are just creating a new file. Time zone, we are creating timestamp for the name of the file or the Stego file that will be created. We are writing the information inside that file, and finally we are reading this file one more time to do the plotting. We are painting or plotting these two signals together to see if there is a significant difference. Finally, over here we have the metrics, the mean square error, the PSNR, the SNR, and the number, the bit error rate, the number, and the ratio of the error, and that's it. Here we are writing a small report in text format, so it's just easy. So all of this before this point is just reading the file, and all of this after this is writing the file, and the embedding process is this single line of code, just a simple replacement or substitution. Over here is just writing or creating the new signal in the directory that we are using. That's it. So I hope it's helpful. The same type of file is used at the retrieval. If we are using the decode, it's even easier, because what we are using over here, why it's open in Notepad++. Okay. If we are using, if we are doing the retrieval, we are just doing the bit get. This is the simple. This is as simple as that. We are just using the bit get after we read the audio signal or the Stego signal. Just reading the length of the file, and then we are using the verification. Maybe this one is missing some parts. But anyway, this is just based on the bit get function. I'm really sorry for any extended explanation. I hope it was helpful, this session, and may inshallah, Allah bless you and your accept your deeds during this this month. And I wish you all the best, inshallah. Thank you very much for your time.
Thank you, thank you, thank you, Ahmed. Thank you once
Sure.
again, and thank you to all the participants. Prof.
Gambar.
Okay. So I think before we end the session, we
Yeah.
should get the proof, you know, the picture proof.
Yeah, sure.
Okay, yeah. So can everyone turn on their camera now?
Okay. I think I will join from. Oh, okay.
Which one is better? Gallery together mode, is it? Okay, wait, let me change. Uh, okay. Okay, let me snip the photo. Okay, 1, 2, 3. Once again. Prof, we haven't seen you. Prof Norita?
Saya buka video tapi tak nampak
Tak ada.
Kejap. Masih tak nampak
Tak ada.
Macam mana? Tak apalah. Saya pun tak tahu benda yang saya usik.
Sekejap, saya tukar Lush Gallery. Okay, sekali lagi Once again. Siapa create backup dia? Okay, once again. 1, 2, 3. Okay.
Thank you.
So I'll be sharing this one later. Thank you again, Ahmed.
Thank you very much, Doctor.
Thank you for the
Dr.
time.
Ahmad.
Thank you very much. Thank you.
Okay, thank you everyone. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullah.
Bye.
Bye, Dr. Azdi.
Ramadan Kareem.
Ramadan Kareem. Thank you.